This is a limit example, kind of classic, where you're asked to find the limit as x approaches 0 of 2 plus x to the third power minus 8 all over x. This is very, 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 very typical. It is actually an application of the limit definition of a derivative for anyone who's more familiar with limits and derivatives. I've gone over limit definition of a derivative, so while I go over this example, why not make a little bit of a connection to something I've mentioned before. So we've talked about the limit as delta x, or the change in x approaches 0. The change in x is your denominator when you deal with slope. The numerator is the change in y, and the denominator is the change in x, right? So the change in y, you could put y2 minus y1 using function notation, f of x sub 2 minus f of x sub 1, right? So change in y over the change in x, and I'm literally going to write change in x. To find the slope, you need two ordered pairs. You need two separate points. The first point we use is just plain old x. So here I normally have an x. F of x is the y value at x. And here I really did have minus x happening, I promise. My y value, my other y value, my other x value is actually a little bit shifted over. It's x plus a certain amount. How much did I add to x? Whatever the change in x is. So x plus delta x was my new x value. So my first x value was 5. My change in x is 3. Then my other x value is 8. So you would have 8 minus 5. On bottom, you'd end up with, if you open up this parenthesis, just delta x, right? On top, you still have to put in that other x value. And this will all make more sense, especially if you've already done the limit definition of a derivative and come back and look at this. It'll make things a lot clearer. So what we have up here is the change in y, two y values being subtracted. That's how you find the change in them, over the change in x. And ideally, we want these 2 points that are on our function to get really, 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 really close together. So instead of us finding the slope of some secant line, a line that crosses through a function at 2 points, at 2 distinct ordered pairs, that secant line will slowly, slowly evolve into a tangent line, which we've discussed also, and the slope of the tangent line gives us the rate of change of a curve at a special instant, an instantaneous rate of change. Now, if my function ends up being some sort of a cubing function, x to the third power, and if my delta x, or my x value is, say my x value is 2, x is 2, and I'm dealing with x to the third. Here's a little side example, show you where it all connects. My function is x to the third power. My first x value that I use is going to be when x equals 2. And instead of delta x, they kind of reversed it, and my delta x just becomes x. It's just notation. My delta x is equal to just x in this case. So when all is filled in, on top, you end up with f of x plus delta x becomes f of x plus 2, or 2 plus x rather. That's my x and delta x, minus f of x, my x was 2, f of 2, all over the change in x, which is x, and then that limit out front, limit as, well, instead of delta x, they're just using x, they're just changing up notation, approaches 0. If I fill that in, x plus 2 or 2 plus x, evaluate that for my function x cubed, do you see it's going to be x plus 2 quantity cubed? And then that is going to really be 2 cubed over x, but 2 cubed is equal to 8. So that right there is essentially the problem. I see it because I have more practice. You guys won't see it because you don't have as much practice, and you also haven't done this true limit definition of a derivative yet, so you're not going to catch this all the time. So I see it happening, and once you know what it is, it kind of helps guide you along the way. But in either case, when we asked to go over this example, it's really to review Pascal's triangle again. Pascal's triangle, you should know how to make without too much trouble. The top row is actually row 0, which is just the number 1. What numbers are in row 1? 1, 1. The next row? 1, 2, 1. And the next row? 1, 3, 3, 1. Okay, so your row number, which is row 3, is actually the 4th row down, and it'll have 4 terms in it. So we're going to use 1, 3, 3, 1. Then all you have to do, please retain this, remember it, practice it, do whatever you have to do, because otherwise you have to keep on multiplying 2 plus x, 2 plus x, 2 plus x, however many times, and that's just ridiculous. Okay, we should all be way past that. So if we're going to do this example, you rewrite limit every step of the way because you haven't taken the limit. Think of it as a square root. You keep putting the radical on something until you actually take the square root. Once you actually take the square root, then you can get rid of the square root. You won't leave it on top. Now, I'm going to take this 1, 3, 3, 1. I'm going to use those. Those start as my coefficients. They end up not being the coefficients when all is said and done in this case, but they start as my coefficients. Next thing, here's the 2. It could be the 2 or the x because it's addition, commutative property. Next to this 1, what gets written if I'm taking this 2 into consideration right now?
2 to the 3rd.
Yes, 2 to the 3rd. And then this one gets a 2 to the 2nd, 2 to the, and 2 to the none, right? Then we work backwards. This one gets a, right, we take the second thing and work backwards. So x to the 3rd, x to the 2nd, x to the 1st, and x to the none. If it's a plus sign, which it will always be when you're dealing with the limit definition of a derivative, it's always going to be a plus sign. If it's a plus sign, you get plus between each of these expressions. If it's a minus sign, whatever way you memorize it, really you could say the first term is positive, and then you have a negative, positive, and you alternate until the end. This -8, don't alternate, it's just whatever was there to begin with. Or if you memorize it as the second term to an odd power, if that's minus, is when it'll have a minus. So this is x to the 1st, so it'll have a minus sign, it'll be negative. X to the 2nd was negative x, so it would be a positive, and so on. Then we're just going to clean up, evaluate, cancel, reduce, and we're good. That's all it is after this. After this, it's just algebra. Really from the beginning, this is just algebra because you're not the one setting up and taking the limit yourself, okay? Here, 2 to the 3rd times 1, so I have 8 plus 4 times 3, so 12x. This is, correct me if I make an algebra mistake, plus 6x squared, and plus x to the 3rd minus 8 all over x. These examples, every single time, the second part, okay, this is what I mean by the second part. Well, everything is going to cancel out with something from over here. -8 plus 8, we're good to go. This x will act like my delta x. That's our little troublemaker. It's giving us our problem. Why is x in the denominator giving us a problem? Right, we can't have 0 in the denominator. We can't use direct substitution right now. Direct substitution would make life easy. Can't do that. Now, how can I get rid of this x? What has to happen in the numerator? Right, we factor out the x and then cross out, which is also known as reduce. So 12 plus 6x plus x to the 2nd. Again, correct me if I make some silly mistake. Here is, I have the x over the x. Devil is gone. Little troublemaker is no more. Now we can do direct substitution. Direct substitution tells us we're going to fill in 0 for x. We have no discontinuities. It's a nice continuous polynomial. Direct substitution is good to go. If I fill in 0, what do I end up getting as the answer? 12, okay? If you wanted to show work for yourself, for future you, when you go to look at this, when you're doing a summer assignment, or when you get back into the school year and you're in calculus and you're expected to know it, you might want to show what you did there. Maybe you draw an arrow and say direct substitution, okay? But either way, your final answer ends up being 12, all right? So that was this first example. Next example that we have to go over, a little bit more practice with limits again. So here we have a piecewise function. What makes something a piecewise function?
Multiple functions.
Okay, multiple functions. What else? Elaborate on that. What do you mean multiple functions?
There's different styles of functions.
Okay, well, they could all be, these are all trig functions, but there's a lot of functions, but you could have one graph with a lot of functions on it, but a piecewise function will have pieces or set intervals of more than one graph. So that's where the piece part comes from. It's many pieces. So you could have 2, 3, 4, just more than one, and you'll have set domains for each of them. Now sometimes this could be sine is everywhere except between there and there. If sine was everywhere except this interval, then it would go from -infinity up until that, from 0 up until infinity. So sometimes you see stuff like this. I'm not going to use a regular graph that goes out, 10 tick marks in each direction when I'm dealing with trig. Looking at these trig functions, how should I count out my tick marks over here on the x-axis? What should we do?
Should we start from 0 or like left to right?
Either way, just what kind of numbers are going to go, what increment are we going to count by, how far out should we go? Up by pi over 2. Good, because the period of sine and cosine is 2 pi over b. B is the coefficient in front of x, which is 1. So the period is pi. And we have different quarters of each period. So we like to divide our period by 4. So 2 pi over 4, which is pi over 2. So whenever I count by 4s, I like to go out the fourth one, then find halfway, and then half of each of those so they're evenly spaced. This way I can kind of fit everything nicely. And then I just mimic that on the other side. So we're good with that, right? Here's 2 pi, here's pi. If you aren't so good at graphing trig or you forgot how, I do have like very in-depth videos that I made on Doceri from a year or two ago on the YouTube channel. So if you wanted to look at those, lots of examples there. And it was sort of there when we were doing summer work. Okay, what about my y-axis? What should I be putting on the y-axis for this example?
You have 2 negative pi's.
2 negative pi's, I'm smart. This is negative pi over 2, thank you. Okay, what else? Y-axis, what should I put? 1 and negative 1, yeah. Because my amplitude or there's no stretch on this and it normally goes up to 1. So 1 and negative 1 is good. Now I'm just going to color coordinate. Sine is over here. And that one is going from negative 2 pi, closed at negative 2 pi, to 0, open there. So this is where I'm drawing sine. Where should I be drawing the output value for sine at the x value of negative 2 pi?
0.
Okay, good. Close point at 0 as an output. How about here at negative 3 pi over 2? What's the output?
1.
Good, it's going to be positive 1. Obviously, this is not drawn to scale, but we stretch it so we could see things the way we'd like. Then at negative pi, good, and negative pi over 2, negative 1. And at the x value of 0, we get open at 0. Good. So here I have this. Now, also, let's just make sure we're really aware of our concavity, because in calculus, when you start doing derivatives, you're going to do the first derivative test, which tells you when a function is increasing or decreasing, and you're going to do a second derivative test, which tells you concavity. So you have to be able to, you'll have the information, oh, your graph will be concave up from negative pi over 2 until 0. You'll have to use that to draw a function. So you have to know what this concavity looks like. Concave down will look like this. It's all about which way the graph is curved, okay? Now I'm going to draw the piece that is our cosine. And we have cosine of x. At 0, where do I start my cosine of x?
1.
At 1. So you have to memorize these outputs. You want to know them really well. How about, what pattern do I follow? I go from 1 to what? 0, then 2. Mm-hmm. 0 again, good, and back up to 1. And they were closed on both ends this time, right? And then again, here, this is where people draw very pointy graphs. It should not look like an absolute value function. Concave down. This pen's not too good. Concave down over there. Then, I'm going to use the light blue marker since I already picked light blue, but concave down is here, and concave down is also here. So if you see I curved it a certain way, maybe a little over the top, dramatic, and then here it's concave up, okay? So there we go with our cosine. So that part's done, it's graphed. You don't stick an arrow at the end, do not overextend it, because it is a set interval for this one. Now, in the directions we're asked to analyze any one-sided limits. You could take a one-sided limit anywhere, you could take a two-sided limit, that's fine, but what are the good places to really be concerned with one-sided limits in this example? What do you mean, say evens? Oh, the ends. I thought you said the evens. Like the evens, what? The ends, okay. And where would you consider that? So limit as x approaches what number, for example? Sure. If we're approaching negative 2 pi, what side should we approach it from? Good. You want to be able to approach it from the right. That means this little plus sign. You can't approach negative 2 pi from the left because there is no graph here. It's like not having any road. So when you're using Google Maps or some other kind of a GPS and it tells you turn left and like there's a river, you're like, this is not good, right? So it tells you to go somewhere. You're not going to turn left into a building. So you can't go somewhere where there isn't any road. The road is the function. That's what you're allowed to follow. So if I approach negative 2 pi, for example, from the right, what is the limit going to be?
Right would be
0. No, it does exist. You're approaching from the right. Now, you don't have to start out here and be like, oh no, I'm stuck. When you approach from the right, you want to get really, really close. Sometimes you use the phrase arbitrarily close. So you want to get really, really close, because even if you start right here, right there, between this x value and negative 2 pi, how many numbers are there?
a whole lot.
Whole lot, infinite, yeah. So even though you think you're close, there's still an infinite number of numbers. If you keep saying I'm going to get halfway closer, halfway closer, halfway closer, you're never going to get there. If you just say I'll do half of what's left, right? So I approach from there, get closer and closer, I'm going to get 0. Where else can I take a one-sided limit? Let's just make, do 1, 2, 3 more.
2 pi.
As x approaches 2 pi, okay, and what side do we want to approach that from?
The left.
From the left, that's the minus sign. And I write f of x, instead of writing this whole function, we write f of x and we define f of x elsewhere in the problem. And what is the limit as we approach 2 pi from the left? Positive 1, good. Where else can we take a one-sided limit?
0.
Sure, so if I take the limit as x approaches 0 from the left, what do we get?
Doesn't exist. Oh, no. 0.
You get 0. An open point, okay, like this, doesn't matter. A limit is not where you get. A limit is what it looks like you're approaching. Where does it look like you're going? What number, what output, what y value are you getting closer and closer to, right? So when you pretend to throw a ball, or even if I just cover this, right? Where does it look like we're going? If I had to guess, I would say we're going to 0, right? You get what I'm saying? Okay? It doesn't mean you have to get there. It's like, ooh, surprise, you didn't really get there. It's a limit. So from the other side now, because this one we could approach from both sides, the limit as x approaches 0 from the right of f of x. That answer is positive 1. Now, when we had our definition of continuity, which I had typed up and given to you, I could actually find that right over here. The definition of continuity in Algebra 2, what we say all the time is like, oh, it's continuous if you can draw it without picking up your pencil. You're not going to know every function, so you're going to need a better definition of continuity. So we have these two definitions that are typed up for you in the first packet we did with all the function practice, limit practice, and continuity practice. So these two definitions both say the same thing. One kind of says it using kind of double negatives. It doesn't equal, does not exist. This is in certain textbooks, and certain authors, mathematicians, professors, whoever might use this one. I kind of like how this looks a little bit better. But it says in order for f to be continuous, because like I said, you're not going to know what every function looks like at a, some given x value, the following three conditions must hold. F of a is defined. So I want to know, is this, by this checklist here, and this is going to be something you'll be expected to do in the future. So I'm going to write continuity checklist at x equals 0. I'm checking, is this continuous at 0, all right? So the first thing says f of a is defined. So f of 0 is defined. Can I put a check mark or do I put an x?
We're good.
We're good. We are good. Now, does it ask us to say what it is? No, not right now. But in number 3 on this checklist, the third thing down, it will sort of ask us to know that answer. What is f of 0?
1.
Yes, it is equal to 1. So I'm just going to put a little 1 in parentheses. That is how it's defined. So a function being defined, that's when the closed or open circles matter. Next thing on the continuity checklist. So if you're ever asked in calculus, prove or explain why this is or is not continuous, you need to follow this checklist, okay? So number 2, the limit as x approaches a of f of x exists. The limit as x approaches 0 of f of x is supposed to exist. Does it?
Nope.
No, it actually is DNE. Why is it DNE? The left side equals, it's two different answers, good. The left side is going to be approaching 0, the right side approaches 1, so that's D&E. So we already failed right there. If it did exist, and that did equal 1, number 3 would have to be true. So sometimes you'll get both of these to be true. Number 3 says the limit, which is, this is essentially number 2, the limit and f of a, number 2 and number 1, the answers to both, are equal to each other. Are equal to each other. That is when you're not continuous. But we already know we're not continuous up here. So if one of them fails, you're automatically done. Okay? 1 does not equal D&E anyway, which is ridiculous, right? So of course that will automatically fail. What will an example look like? While we're on this, let's go above and beyond. What would an example look like that does meet both of the first 2 criteria but fails the third one? The function is defined. We can even use 0 again. We can make up a different function. The function is defined at 0. The limit at 0 exists, but the function's value, the output, and the limit answer are not equal. Can you describe what a function would look like that would meet the first 2 criteria but fail the third? Okay, there will be a hole. That's true. So let's get a little bit started here. So I'm just going to draw a mini little sketch down here. X-axis, Y-axis. Where do you want me to plot the hole for right now? Just make up a location for me. Over 1. Well, if I'm trying to do it at 0. Better. So 0, 1 right there, okay? That's 2, negative 1, negative 2. So there's 0, 1. I drew a hole. All right, what else can I make happen over here? I'm going to do pink on the left again. I'll do blue on the right. So what can I draw over here? Tell me anything to sketch.
Parabola.
A parabola. So vertex up here, vertex down here, imaginary vertex down here. So if I had some sort of a parabola, yay, boom. I have that. What else? Horizontal line. Where should I start this? So that's on the right side in blue. Where should I start my horizontal line? Where should the horizontal line be drawn at?
1.
At 1. So this being in pink, I could also kind of draw it in blue, right? And then I have a horizontal, I picked up this pen again. I have a horizontal line right there. All right. What else?
You have a point at -2.
Have a point at -2. Now, why is that important? If we didn't have that point, why would that be important or affect this? Go ahead.
There'd be no f of x.
Right. You'd fail the first thing on the checklist, okay? So a little cut off there, sorry. So first thing on the checklist asks you, does f of 0 exist? Is it defined? Is f of 0 defined? Yeah, it equals -2, so it is defined, check. Number 2 asks you to find the limit as x approaches 0 of this function f of x, which I don't know what it is right off the top of my head, but does the limit exist?
Yeah.
Yeah, it does. What is the limit? 1. So check and check. Last thing on our continuity checklist basically says that the function value, the output, f of a, f of whatever you're approaching, must equal the limit as we approach it. Does -2 equal 1?
Yes.
The big answer is no. So that's where it fails, so that's why it's not continuous. So you can't just say it's continuous or give a definition. Think when you explain something to someone who doesn't know what you're talking about, you can't just be like, you just know it is because. Like explaining factoring to someone who can't do it in their head, it's always a nightmare. So you have to actually show them a method and have a more concrete way. So we're just tying in definition of continuity to this example so we could kind of, like I said, kill 2 birds with 1 stone. All right? Here in this example, if we take the limit as x approaches 0 of this expression over here, this function, 1 over x plus 2 minus 1 over 2 all over x. It's another limit definition of a derivative behind the scenes, change in y over change in x, but if you wanted to compare this to another example, the earlier one with the x cubed, go ahead and try to compare it, but we're just going to go from here. If you tried direct substitution and you filled in 0 into this expression, what do you end up getting as a result of filling in 0? Well, what do you first, right off the bat, it looks like what? 0 over 0, right?
Yeah.
Yeah, so 0 over 0, which looks like our division sign, that is not 0 and that is not undefined. That is indeterminate form. Oh my gosh, can I spell? Not right now. Indeterminate form. Okay? So that tells me nothing. It means we need to do some fixing over here. So when I see 0 over 0, I see a division sign. It tells me I'm going to divide out or reduce out this problem. The problem is really the 0 on the bottom, not so much the 0 on the top. The other thing I keep showing, 0 on top is okay. 0 on bottom, no, right? So if I want to clean this up, trusting your gut and trusting your instincts, thinking of things you've done in algebra, done with trigonometry, how can I clean up this big, ugly, gross expression? Sometimes conjugates come in handy. Conjugates more so you want to use with rationalizing, so if there was a radical involved. We don't have a radical involved here, so that's not going to help us clean this up so much. What else can I use? What else is another annoying feature of this function over here? The fractions. It's basically a compound, complex fraction. We have fractions within fractions. So how can we clean up all this excessive fraction? Good. Multiply on top and bottom by the least common denominator. I kind of make this hamburger situation, if you recall. So I multiply on top and bottom by the least common denominator, which will be what? What's the least common denominator? Any day. 2 times x plus 2. Good. If you distribute that through, just as I write this out, we can keep up with this. Limit as x approaches 0. What do I get here? Think of partial fraction decomposition even. What do I get here? 2 minus, what do I get here?
X plus 2.
But it's in parentheses. I'm going to distribute, so I'm going to get x minus 2. And you're not going to distribute on bottom. So 2 times x plus 2. And then you could just take it from there. All right? So this x and this x will reduce. On top, you're left with negative 1 over 2 times x plus 2. That x on bottom is now gone, the problematic one. And now you could just take the limit and it'll be fine and you'll get an answer. X approaches 0. That's negative 1 over 2 times 2, which is negative 1 over 4. And that is your answer. That's how you do every single one of these.